This is Jody Trana with Chapter 6, Part 1 of Business Finance. Let's do a quick review of Chapter 5 and the concepts that we learned there. We learned about the time value of money and how to compound a lump sum and how to discount from a lump sum. We had fairly simple problems to solve, such as compounding problems like, if you had $5,000 today, how much will it compound to in 6 years at the rate of 10%? And we had discounting problems, just using lump sum numbers, such as how much should you deposit in the bank today for it to grow to $10,000 in 16 years at 3%. But problems aren't really this simple. Many times we don't deal with lump sum problems. It is fairly common for us to need to work with annuities rather than lump sums. Annuities are a series of equal dollar amounts that are made at the end of consistent points in time, such as every week, every month, every quarter, every year. And these amounts we can also determine as a future value, or we can calculate the present value. We also now will be adding payments to our calculations. As we're working with annuities, we may be asked to identify any one of these missing elements, such as the number of periods, the interest rate, the payment amount, the present value, or the future value. The first type of annuity that we're going to work with is an ordinary annuity. With an ordinary annuity, the annuity happens at the end of each time period. So here you can see our annuity happening at points year 1, year 2, year 3, and year 4. They happen at the end of a period. First of all, let's work through a problem. Here's an ordinary annuity problem. How much money will you accumulate by the end of year 5 if you deposit $5,000 each year for the next 5 years in a savings account that earns 6% per year? Whether we are compounding or discounting, the first thing to do is to always draw a timeline. This will help put everything into perspective. The second thing we'll do is to identify the elements. The third is to solve the problem, and the fourth is to analyze. So let's take a look at the timeline here. You'll see that our time period begins at 0, and we have all the years through 5 written on here. We also have our cash flow amounts, the $5,000 that each year will be deposited towards our future value. And that is our missing element that we're looking for. We have an interest rate of 6%, and all of these items are going to go into calculating our future value. I hope you remember that the financial equation to calculate future value is the present value times 1 plus the interest rate. If you take that interest rate to the nth power, then you can determine your future value. We can use this same sound theory of math and apply it to calculating an ordinary annuity amount. We're going to work this problem from future value back to present value. So that means we're going to start with the $5,000 annuity that gets deposited in year 5. Think of it this way. If you were to deposit $5,000 on January 1, let's say, or December 31 for that matter, how much would you have on January 1? You would have that same amount. There would have been no interest accrued. So for this one annuity, the $5,000, it is worth exactly that, $5,000. We need to collect that number, and that's why we have it written over here to the right, and we're going to add to it the compounded annuities of all of the other 4 years. So now let's look at year 4's annuity of $5,000. If we were to calculate the future value of the annuity that was deposited into the bank on year 4, it would compound interest for one period, for 1 year. So you can see here our equation is to take the $5,000 present value at year 4 and add just 1 year's of accumulated interest by multiplying it times 1.06. Now over to the right, you can see that we have our $5,000 that came from year 5 and our $5,300 that compounded from years 4 annuity. Now we're going to take the annuity for year 3 and compound it. This time we compound it for 2 periods. So you can see we would take the 5,000 and we would multiply it times 1.06 twice. That gives us a future value for the annuity in year 3 of $5,618. Year 2's annuity of $5,000, that can be compounded as well for 3 years. And you'll see here that we've taken the 5,000 and multiplied it times 1.06 3 times for a total of $5,955. We have just one more period to go. When we take year 1's annuity of $5,000, it will compound for 4 years. Therefore, we take that number and we multiply it times 1.06 4 times to get our amount in year 5 of $6,312. What we've done here, rather than calculating these as a payment or a real annuity, we did 5 separate lump sum calculations. We could do this for annuities, but it would just get rather complicated. Think about if we were trying to figure out how to do this for a 25-year cycle. It's much easier to use your calculator or Excel to figure out these complicated problems. There is a math equation, as you can see here, that we can use to calculate annuities and the future value. The way that we calculated it comes up to the same amount as using the equation, which is $28,185. Now let's try calculating the present value of an annuity. How much of a loan can we get today if we can pay $500 yearly for the next 5 years at 6%? Here you can see we're calculating this again as if it was 5 lump sum payments. The missing element is the present value, and each one of these $500 could be treated as if it was a lump sum. We can discount each one of these $500 as a lump sum back to time period 0 using this equation shown here. So year 1, $500 divided by 1.06 gives us a present value in year 0 of $471.70. In year 2, we take $500 divided by 1.06 to the second power because it's the second year, and that amount is $445. Each year can be calculated separately as if it was a lump sum, coming up with the present value of each one of these lump sums, totaling them up to identify the present value of this annuity of 5 payments of $500. And the loan that we could get today, if we could make this kind of a payment, would be $2,106.18. Now I'm showing you the math equation to calculate one time using the annuity calculation. We're still going to choose to use our financial calculator or Excel. Once you get the hang of them, annuities are no more complicated than calculating lump sums. But there are some things that do complicate them that you need to watch out for. Sometimes you'll be asked for non-annual annuity payments. That might be quarterly payments or twice a year payments. Sometimes you might have a down payment that will change your present value or your loan amount. Sometimes you might have an annuity that doesn't start immediately but starts in the future. Sometimes you have elements that aren't given to you and you have to calculate them. Sometimes you'll have multi-step processes. Maybe two things happen, such as you have an annuity and you have a lump sum together. And then finally, sometimes we have annuities due rather than ordinary annuities. And annuities do happen at the beginning of periods. We need to handle those differently. Here's a graphic that should give you an indication of the difference between an ordinary annuity and an annuity due. With an ordinary annuity, the payments happen at the end of the year. So here you can see there's no payment at year 0. The first payment happens at year 1. The second payment at year 2, the third payment at year 3. An annuity due, all the payments happen at the beginning of the periods. So here you'll see the annuity payment happening at period 0, and the second payment happens at year 1. The third payment happens at year 2. When we calculate annuities due, we have to be careful to calculate them a little bit differently. Excel and financial calculators both give us a method to do this. We just need to remember to do it. We're going to take a quick jump back in time so that you can remember how an ordinary annuity is handled. You'll see here that each one of the annuities is calculated at the end of the period. And notice that in the 5th period, we talked about how there was no time for any kind of compounding because the 5th payment is paid right at the end of the 5th year. Now take a look at this timeline for an annuity due. You'll notice that the final payment is made at the beginning of the year instead of the end of the year. So there is some compounding that takes effect in the final payment of an annuity due. If this had been an ordinary annuity, year 4 would have had a payment instead of year 0. The year 4 wouldn't have had any compounding. Therefore, we would have had one less year of compounding. So with an annuity due, another way to think about it is that you have one additional year of compounding than with an ordinary annuity. Taking a look at the present value of an annuity due, you'll see that the opposite is true when we discount. Since there is cash flow in year 0, there's discounting for one less year. It can be much more accurate to leave the calculations to your financial calculator or to Excel. On your financial calculator, there's a button BGN, which stands for beginning. and it changes your annuities into the beginning of the period rather than the end of the period. In Excel, now we can use the type function, which comes at the end of your future value and your present value calculations. The type is normally a 0, but when you put a 1 in for the type, then it will calculate as an annuity due.